Okay, in this video I want to discuss some basic properties of logarithms. Okay, let's go ahead and do this. We saw this in the last video when we introduced logarithms. B is a base, right? So that means it's positive but not equal to 1. Okay, b to the x is equal to c, right? If and only if what? X is the logarithm base b of the value c, right? Okay, these are saying the same thing in two different ways. Okay, now if I came up here and replaced x literally by this expression here, logarithm base b of c, you see what I would have is b to the logarithm base b of c is equal to c. This is going to be a way of thinking about definition of logarithms, right? It's the power I have to raise b to get c, right? It's the exponent. The power I have to raise b to get c. By the way, we'll be discussing this. C is going to have to be greater than 0 because remember the value of any exponential is going to be what? Positive, right? Okay. Another expression here I want to write down. The logarithm base b of b to the x power equals x. Now x can be any real value here. Remember the domain of an exponential function is any real number. Okay, the logarithm base b of b to the x, what would that be by definition? It would have to be the power I would raise b to get b to the x. Well, that must be x, right? Because b to the x is equal to b to the x. By the way, I would remind you that exponential functions are 1 to 1, so this would be the only value for which that would hold, right? So these two together you can think about are defining what it means to be logarithms. And now I want to think of this in a slightly different way. If I said f of x is the function b to the x, okay, so that power function, and I said g of x is the logarithm base b of x, then if I was to compose the functions this way, f composed with g of x, that's f of g of x, that's f of logarithm base b of x, right? I just substituted the formula in there. What does f do to what you put into it? It takes the base b and raises it to whatever powers inside those parentheses. So that would be what? B to the logarithm base b of x, which we just showed up here would be what? X, right? I replaced c by x in this particular equation because I want it to be variable. I want to think of it in a varying way. Here I was thinking of c as a constant here. Okay, now what if I go ahead and compose the functions in the opposite direction? I go g composed with f of x, g of f of x. So that would be what? G of b to the x power, because that's what f of x is. And then it would be the logarithm base b of b to the x, which is x, right? That's what we have in that box right there. So no matter which way I compose these functions, I get what I started with, right? I started with x ultimately and ended with x in both cases. What does that mean about f and g? That means they are inverse functions, okay? They've got to be inverse functions. Each one undoes what the other did to x. Think of it that way, okay? All right, so they're inverse functions of each other. So there I've made that statement explicit without using a reference to f or g. Okay, for example, 2 to the x power versus logarithm base 2 of x. These are inverse functions of each other. Okay, and we're going to see that in just a second here when we look at a graph here. I graphed this on Desmos so we could compare. I also created a little table of values so you could see this happening. Okay, before I do that, and we shall see this illustrated in the graph here, b to the x, remember, that's an exponential function, in particular a power function. It's therefore what? 1 to 1, continuous, and smooth, meaning no corners. What was its domain? All real numbers. And its range were what? All positive real numbers. It also had a horizontal asymptote being y equals 0, that is the x-axis. Okay? I claim the following, that the logarithm base b of x is 1 to 1, continuous, smooth, with domain 0 to infinity and range minus infinity to infinity, and it has a vertical asymptote instead being x equals 0, that is the y-axis. Now let's see why this holds here. Now before I do actual table of values, let's take a look here. Okay, I graphed this on Desmos here. Let me hold it up close. Do you see I've got y equals 2 to the x, that's an increasing function, and I've got some various points sampled there on that. And then I have what? Graphed with it in red there, y equals the logarithm base 2 of x. I also threw in the line y equals x. Do you remember that graphically you can get the inverse of a one-to-one function by taking the graph of it and what? Reflecting it across the line y equals x. Well, if you look at these two graphs, they indeed look like what? Reflections of each other across the line y equals x, illustrating that they are indeed inverse functions. Now, before I talk about the individual points here, let's talk about what we notice from this graph. It is indeed true that what? My logarithm function here is continuous, it's smooth. If I was to project it onto the x-axis, you see I would get what? All positive real numbers from 0 to infinity, not including 0, and of course not including infinity. Okay, but if I was projected onto the y-axis, believe it or not, this thing just keeps continuing going upwards like that. So I'll put a little arrow on that. If I was to project this onto the y-axis, I would get everything from minus infinity to infinity. I would get all real numbers, okay? So that's what I was mentioning right here. Now, the way we can see that is another way of thinking about inverse functions. Do you remember? Another way we can think of inverse functions is, well, a function consists of a bunch of ordered pairs, right? All right. Now, you can get the inverse of any relation by doing what? Taking the set of ordered pairs and reversing the order of the elements in the ordered pair. For example, here I get what? 2, 4. Its reversal would be what? 4, 2. Here, the point 1, 2 lies on this function, 2 to the x. Its reversal, 2, 1, you notice lies on the logarithm function there. Now, that's exactly why this is happening here. If I'm going to interchange all the ordered pairs, what happens here is the domain of my original function becomes the range of my inverse function, and the range of my first function becomes the domain of my second function. Also, a horizontal line like y equals 0 becomes what? X and y are interchanged, so it becomes x equals 0, which is a vertical asymptote, a vertical line. Okay? So that's exactly why that's happening here. Let's just double check. I took these points on the graph here. Let's write them as a table of points here. Okay? I've got my x values here, and I've got the corresponding function values in each case here. Okay, so we took these. Okay, if x is 3, 2 to the third power is 8. X is 2, 2 to the second power is 4. 2 to the first power is 2, and so forth on down the line. Over here, I've done this with logarithms. The logarithm base 2 of 8 is 3. The logarithm base 2 of 4 is 2, and so forth on down the line. Notice that this would be my ordered pair then, right? On this graph, it would be 3, 8. But over here, the logarithm base a of 8, base 2 of 8 is 3, right? This is saying what? 2 to the third power is 8. This is saying 2 to the third power 8 is a different, in another way, it's saying the logarithm base 2 of 8 is 3. Okay? See how they're really saying the same thing in two different ways, but what the independent variable is, you can think about, or the independent value, is been interchanged here. And you see this happening all the way down. So in fact, 2 to the x and the logarithm base 2 of x are inverse functions of each other. And in general, b to the x versus what? Logarithm base b of x. These are inverse functions of each other. Okay? So that's something we'll bear in mind. Okay? And once again, I also want to mention that's one-to-one then, right? If the original function is one-to-one, so is its inverse. If this passes both the vertical and horizontal line test, so does what? The graph you get when you interchange all the elements in the ordered pairs. So this passes both the vertical and horizontal line test. Okay? All right. Let's talk about some properties now. These are things we really need to remember for the stuff we're going to do in the future. Okay? These are not difficult here. And I'll explain, I'll actually prove these for you. But remember that logarithms are exponents. Okay? Logarithms are exponents. Okay, I'm going to call this the product rule. Now, x and y are positive, so that means all these logarithms will exist. Okay? Remember, you can't take logarithms of negative numbers. Okay? Or zero, for that matter. You can only take logarithms of positive numbers because we said what? The domain is 0 to infinity. Okay, not including 0. Okay, anyway, so I mentioned that up there. That's just saying so all these things exist. Okay, but here's the product rule. Logarithm base b of x plus logarithm base b of y is the logarithm base b of the product of the two. Okay? Okay? Product of the two. Now let me see. Let me explain just kind of verbally why that's holding before I give you the formal proof. You think in terms of a common base. What do you do when you take a product when you've got a common base? You add the exponents. These are exponents, and you're adding the exponents. Remember, this is saying basically the same thing we saw here. Okay? There my base is called A, though. Oh well. Okay, the quotient rule. Okay? Logarithm base b of x minus logarithm base b of y is the logarithm base b of the quotient of the two. Okay? All right. Well, once again, if you're dealing with a common base and you take a quotient, what do? You take the difference of the exponents, right? These are exponents. You're taking the difference of the exponents. Here's another rule. I wrote this kind of backwards from the other ones. But the logarithm base b of x to the r power, okay, r can be any real number, by the way. I guess I could throw that in here. Okay, so if you're going logarithm base b of an exponential, you can actually do the following here. Okay, I mentioned x is positive here. But you can take r out front as a multiplier. This is times. So it's r times the logarithm base b of x. Okay? Do you remember a similar rule? Power rule for exponential forms here? I'm going to show you where this comes from. Okay? But you want to memorize these things. All right? Now let's talk about proofs of these. Okay? In order to prove these properties that we're going to use in the next section, I'm going to go ahead and remind you of a couple of facts. I'm just going to call this z this time because I'm going to be using x and y throughout here. So let's refer to something else here. If z is greater than 0, then b to the logarithm base b of z is z. Okay? All right? B to the logarithm base b of z is z. It's just saying what? The exponential function with the base b and the logarithm base b are inverse functions. They sort of cancel as functions, right? Z has to be positive, otherwise this logarithm up here wouldn't even exist. Actually, they do exist, but they're complex numbers. But that's something you guys will learn about if you continue with mathematics. Anyway, here's another statement I want to do. 2. So these are going to be the fundamental properties I'm going to use in my proofs. B to the x1 equals b to the x2 if and only if x1 is equal to x2. This is just saying exponential functions are what? 1 to 1. Okay? The only way these can be equal is if their powers are equal. All right? Now let me show you how this actually ends up leading to proofs of these things. Let's do the product rule now. Okay? And let's see how it goes. Okay? Remember, I'm trying to show that. Okay, I'm going to show you. I'm just going to play a little trick here. Just suppose I take b and raise it to this power. Just a little something I'm going to do. Okay. Alrighty. Yeah, I just decided to do that. Okay. All right. Well, I could do this. This is times there, right? Wouldn't this be a valid equal sign? Sure it would. If I multiply these two together, because they have a common base, I just add the exponents. Well, that's just what I have over here. All right? Now, wait a minute. B to the logarithm base b of x, that's just x. So this is x times, well, same thing here. That's just y. But hey, you know what's true? B to the logarithm base b of xy is equal to xy. This is true also, isn't it? That's like coming up here and replacing z by xy. Isn't that true? Okay. So, oh, these weird manipulations here. What did this prove? Well, hang on a second here. Look at the first and look at the last. Now, there's equal signs all the way through. So ultimately, these two things I have circled are equal. But wait a minute, these have the same base. So by principle 2 here, what? These two exponents must be equal. Well, what's the exponent on the first one? Logarithm base b of x plus the logarithm base b of y must be equal to the logarithm base b of x times y. Aha, we just proved the product rule. Now, the quotient rule I'm not going to prove for you. I would like you to try that as an exercise. Just give you a hint here. Replace plus by minus, and then what would happen here? I would have a quotient instead. Okay? Give that a try yourself. Let's work the last one, which is the power rule here. Okay, let's look at the power rule. Okay, I'm actually going to start on this side. I'm going to play a similar trick here. So here's the proof of the power rule. Okay, if I was to go b to the r times logarithm base b of x, okay, a little sloppy, I hope you can read that, okay, that's b to the logarithm base b of x, all raised to the r power. How does that hold? Well, do you remember this property? A base to a power, what can you do? You can just multiply the two powers together, the two exponents. Remember, that's a fundamental property. We showed that in power rule for exponential forms. Remember that one? Okay, that's all I'm doing. Power rule for exponential forms. I would take the product of these two and I would be getting that. Okay, but wait a minute. What's b to the logarithm base b of x? It's x. That's x to the r power. Okay. But what's x to the r power? It's b to the logarithm base b of x to the r power. Okay? Using this same principle again. That. Okay? Instead of z, I've got x to the r power. Okay? And now, I've got b to the blah blah equals b to the blah blah. The blah blahs must be equal, right? The exponents must be equal. By principle 2 here, the one-to-oneness of exponential functions. Now, usually we will be using it this way where this r pops out on the outside, but sometimes we won't. But we should be able to go back and forth between these two. Okay, so there are some fundamental principles that we shall be using to solve some problems in the next section. Go ahead and memorize these. They shouldn't be bad. Remember, logarithms are exponents.